My name is Orian, and I work at AppAI, which is a consultancy and projects company that connect research and with production. And today I'm here to talk about my work in the realm of audio. My background is in a computational branch of cognition, which means I love machine learning, perception, psychophysics, and anything that has anything to do with computational human-related models. I don't work alone, and I'm very lucky to be working in my company with the talented Roy Schenberg, that also happens to be here in the audience today. And most of what I'll be discussing here is a part of our collaborative work. So, humans in the loop. Who are those humans? And how to avoid them? It was only after I submitted and was accepted to this conference that I realized that the entire talk is going to be about avoiding humans. And so I think that for most of us here working in data science, when we think about humans in the loop, what we think about essentially is our constant need of getting manually labeled data that represents our human perception. But honestly, when I look deeper and think about humans in the loop, I also see that we are the humans in the loop. Because throughout our day, when I work with audio, I use my perception, my hearing all the time. I cannot avoid listening to whatever is coming in and out and constantly checking the quality of the work I'm doing. Try and imagine a deaf person working in the realm of audio these days as an engineer. They wouldn't be able still to do it because our perception is key. Our own engineering perception is key to our day-to-day tasks. And so these two these two nodes of where humans exist in the loop are the ones I want to address today. And the way I'm going to do it is by telling you two stories. The first one will be about working with weakly labeled data in a breath detector we built. And the second one will be about perceptual quality algorithms we used to minimize the need to listen tediously to many, many examples while trying to improve an algorithm we were building. So let's start with the first one. It is worth mentioning that there are other ways to reduce the need for manually tagged data, which are, for example, unsupervised models and transfer learning. And they are great, but I don't have enough time to talk about everything, so these are the two examples I'll be discussing today. So, weakly labeled data for breath detection. Let's talk about that challenge. We needed to create a breath detector in speech as part of a bigger project. The challenge was data, as it most time is in audio, or rather that there wasn't any. We knew we could, in this case, hire a manual tagger to create a breath data set, but also that this would take time. And we wanted to start working on the algorithm right away. So after some thought and brainstorming, we came up with the following question. What happens when you take LibriSpeech, which is, I'll tell you about it in a second, and subtract all the words from it? LibriSpeech, for those of you that don't know, is an open data set of roughly 1,000 hours of book recordings with accurately aligned transcriptions. We figured, after listening to some samples, that removing the speech from Libri would leave us with breaths and silences, or so we were hoping. And we also figured that breaths are more audible than silences. So just to give you the feel of things, I will play a short sample of what LibriSpeech sounds like. Wait.
We were so deep in the grass that we could see nothing but the blue sky over us.
This is not the right example. Good perception, everybody. Wait. This is the next one, right? This is the right one.
She popped into her new house and sat there comfortably, peering out through the window slits with her sharp little eyes.
So in this snippet, we can see, and also I'll try and pinpoint the fact that there are two breaths which are marked in orange, just before she starts to speak and in between. Sorry. Wait.
She popped.
It's really inaudible here, but you'll have to believe me.
Sat there comfortably, peering.
Okay. That is what we were looking for. And we noticed it exists in, the entire data set. It's just not tagged. So after removing so the library speech has a very accurate alignment of all the areas where there are texts. It's a very common data set for audio. And after removing all the speech from library speech, what we essentially ended up having were many, many tiny snippets that we can see here concatenated. I will explain in a sec, that had either a breath or silence in them. This is a visualization of the non-speech parts we extracted. What we're seeing is a few hundred concatenated snippets, like one row after the other. And between each pair of white lines is a separate snippet that can be one of three things: a breath, a silence, or noise. We were very happy to see, and I can hardly imagine we can see it here, but you'll have to trust me on this, that it is pretty visible to distinguish with our human eyes between a breath and a silence. So, after staring at the snippets image and listening to examples from it, we had a pretty good sense, just by looking at the snippets, which have a breath and which doesn't. This was really a good sign for us. It led us to take we took 10 minutes and quickly manually tagged 300 examples. But we wanted more. So we took those 300 examples and essentially sliced them up to tiny fragments of 20 milliseconds each. And this gave us 4,800 samples on which we trained an SVM, a very simple model. And what we were expecting to see, and is a bit hard, but let's try and see it here, is that there will be two clusters. A shared messy cluster, which will have parts of snippets that are breath and parts that are silence, because in each breath there's the beginning and the ending, which is silence. And there will be a cluster of only breaths. And this is what we see in blue and red here. And the dashed line is the decision boundary of the SVM. So by looking at this, we were already quite positive, but still we didn't have a lot of examples, and this model was making a lot of mistakes. Our next step was to run the SVM model on the parts that are not speech snippets from library speech, extracted from 100 hours of library speech, and create a data set of a huge number of samples, 92,000 samples, comprised of snippets that were either labeled as breath or silence or neither, which is essentially the speech parts of library speech. We used the data set to train a small CNN, and the results did a better job than the SVM in detecting breaths. So the next iteration of this project was to retrain everything again and to re-tag the data set we had using the CNN. And here, we started this iterative process of recreating the data set again, which improved, as I said, our AUC scores from 91% to 94.8. To finish the project, we were pretty happy already with 94.8, but we added, in the end, the tag data that we sent off making. And we also added, we found a karaoke data set named MIR1K that has only the vocals part in it, so we figured the breaths there can help us. And eventually, we brought our ASC scores to be 97.4, which was more than sufficient for us. So that's how we handled the weakly labeled data and created our very much desired breath detection. Any questions about this section before we move on? Yes, okay.
I kind of was late, but why? Why do you need breath detection? You might have said it.
No, I didn't say it.
All right.
I can't really elaborate on the reason I needed a breath detector for. It was, yeah. Thank you for asking, though. It's a good question, right?
Hi, it's a similar question to the previous one, but I won't ask you to tell me why. I'm just wondering if you just want to find out if someone is in the room breathing or near the microphone breathing. Is there a different kind of breathing to the breathing between words or between...
I would say that it is. Oh, I never imagined that this would spark so much curiosity, not to say the exact reason I built this for, but I mean, it wasn't as exciting as you guys are going with this. I love the places you're going. I mean, we're open for any project that is as cool as you're imagining right now. But imagine some sort of an editing algorithm that is trying to improve speech quality somehow, and looking at the breaths and understanding that not being able to notice them causes some sort of trouble, and understanding that if we could only add those breaths to the project, then we will have a far better outcome. Okay. So that was our first part. Let's go to the second one, which is perception algorithms. And honestly, this is such a huge topic that I can't believe I'm even trying to talk about it shortly, but let's be brave together and give it a go. So in this case, we were working on improving an algorithm throughout an iterative process where we had, a repository, different branches to the repository. Each branch was a new version of the algorithm, and we wanted to test out whether the new version is better or worse than our master repository branch. And so we had to come up with a way to work in a team and say, should we adopt a new version or shouldn't we? And to do so, we chose 50 tracks that were our benchmark. They represented the field of all the different missions that our model needed to complete. And with each version, all the team basically had to sit and listen to those 50 tracks and understand whether there's an improvement or not, because it was a very delicate perceptual task, and the different versions sometimes, or even oftentimes, were improving one part of the needed task, but also degrading other areas of what we were working on. And so after doing this for a while, we realized that it would help us immensely to have some sort of scale with the different tracks on them, so that we could know where was the biggest change between the version we're testing and the old version. I mean, just to be able to shift our attention to the areas where the most different differences are taking place. And so I thought this would be an easy task. I thought this is a day of work, just to say if the new version is similar or different than the old version. Not to say if it's better or worse. I thought better or worse, that's hard to achieve. But just saying if it's the same or different, I thought it's easy. Little did I know that not only is it not easy, these are multiple different tasks, because each different challenge here is tested separately, and they don't generalize well. So to measure the quality or intelligibility of a track is one mission, and the artificially generated data or edited data is another. Doing speech is one thing, music is another, live is one thing, offline is another. With reference is one, without is another. You get the point. People get really angry at me on the internet for asking this very general question, so I figured I better have this slide to make the point of saying this is not just one question, it's like 100 of them. But the gist of why is it so needed and it's so hard to generalize is that our audio perception of sound is really not linear, and it's not linearly correlated with the audio signal itself. Human hearing highlights and weakens the auditory signal in a nonlinear way. When a person hears something, that something arrives at their ear and later brain as a mechanical sound wave traveling and vibrating through the air. I like to think of it as three-dimensional ripples all around us all the time. There are maps that correlate between the human perception and the physical audio signal. Here, we can observe the physical metric on the y-axis, which represents pressure level. Loudness is the experience correlated with decibels, which is the y-axis. On the x-axis, we see the frequency, which is pressure over time. Pitch is the experience correlated with frequency. And on the wavy lines on the graph itself are the human experience. But that's not a perfect mapping, and definitely not the whole story of our auditory perception. It's only the beginning. Our brain can add and subtract sounds and most literally play with our head in various ways. I also think it's interesting to note in this graph, which is very famous, it's been researched for 100 years, that the areas at which we have the best resolution, the areas at which we have the best perception for, are those of the human speech, are the areas of the frequencies of the human speech. We are specialized in hearing those frequencies specifically, or maybe it's the other way around. We are created such that our frequency of speech is the one that is perceived best by our ears and brain. And so the way that this was researched and still is researched manually is by mean opinion scores tests, or MOS. And this is the manual human quality tests that are made today and for the past tens of years. Here's how it works. A person is listening to two tracks and is asked to rank how similar or different they are on a 1 to 5 scale. Or they listen to one track and rank what's its quality between 1 and 5. The thing is, that's a pretty hard task if you think about it. People do it over and over again. And there are and it's difficult to do this. And Erica Cooper noted that these tests are consistent within themselves, but she showed really rather beautifully that they are not consistent between each other. That is to say, for example, if a listener rated the quality of a track as 4 in one test, and a different track also received 4 in a different task, that does not mean that these two tracks will get a 4 rating in a third measurement, or that their quality would be perceived as the same. It's important to note that even though MOS tests have many difficulties, they are the product of years of work, and they are still the best that we have in terms of assessing quality or similarity when we come to measure the human perception. And all of the new and shiny neural networks that I'm going to show are trying hard to reach the outcome of those tests. They're the benchmark for the human perception. So to get the gist of comparing two tracks together, let's walk through the very simple intuition of it. If I'm trying to compare two tracks, here it's V1 and it should have been V2, but essentially it's the same track. And I'll subtract them from one another, or I'll correlate them. It makes a lot of sense to think that subtracting them would lead to 0, which will be a good way of telling if they're the same or different, right? The thing is with the audio signal is that if I change those tracks and add a bit of silence in the beginning and in the ending of each of those tracks, or even in one of them, it doesn't matter, and subtract them, then what I'll get will be a very, let's have a listen to what we'll get, but it will sound pretty okay. Okay, let's go here. So this is just the V1 without any changes to it.
We were so deep in the grass that we could see nothing but the blue sky over us and the gold tree in front of us.
And this is the padded silences, the subtraction. The orange track here sounds like this.
We were so deep in the grass that we could see nothing but the blue sky over us and the gold tree in front of us.
So clearly, when we want to measure whether two tracks are the same or different, we need to do some sort of alignment to them. But that's not the only thing we need to do in order to say if they're the same or not. The other thing that we would need to do is to look at them, at each of the tracks as a relative to itself, because we can see that even if we add noise, we're really good, our perception is really good at understanding the signal if we add stochastic noise to it to a very big degree. So we're skipping several iterations of this demonstration, showing how our human perception is coping pretty well with added stochastic noise and all sorts of general manipulations. And going straight to looking at a log-mel spectrogram, which is the most common representation of audio in learning algorithms. The reason that it's so common is that this representation captures the human perception really well. The y-axis represents the frequency and is log scale to match the human ear, and the color scale represents loudness in decibels, also on a logarithmic scale. The idea of scaling the frequencies and loudness on a log scale is used in almost all comparison algorithms, old and new. And we can say that the need to align two tracks and then correlate each section is at the heart of many of the comparison algorithms. So a bit about the contemporary approaches, or maybe start off with what was before the contemporary approaches. With the rise of telecommunication and radio in the beginning of the 20th century, rose a new type of engineering, and there was a need to really assess how well is the audio quality that is being transmitted and is being used. It started messy and became similar to some tools we still use today around the 80s and 90s. It was led by telecommunication companies, as I said, that wanted reliable audio in their radio and phone lines. Their approaches were theory-driven and rule-based. They patented their work and charged a fee, they still charge a fee to use their products to this day. In recent years, there are efforts to change the paradigm into learning algorithms that are black box in nature and rely upon data sets of human ratings. Many of the contemporary works are open sourced. Yay. Okay, so the next part is a bit of a cheat sheet I made when I had to assess the different algorithms. So I'll just share it. I hope we'll all cope with it together. I'll just say that there are many competitors in the race towards quality and similarity assessments algorithms, and I'm going to just talk about a few of them. The ones I'm going to talk about, they capture the different families of approaches that differ by factors I care about. And I believe that if I was to give a similar talk like this next year, the algorithms might be different because they are changing rather fast. So in the first and second row, we see the old school algorithms, or the first one is really the telecommunications one, Peak, PASC, and Polka. These are the telecom comparison algorithms. PASC especially is often used in academic publications as a scoring method in fields such as noise suppression, echo cancellation, and speech enhancement. The second row, VSCOL, is an algorithm by Google, which is very similar in design, but is open source and free to use. It uses perceptually motivated feature extraction, time alignment, and image comparison. It's almost exactly as SSIM, if you happen to know of it, And it generates also a similarity score in the end. What's nice about Viscol, except for it being open source, is that new versions of it work in audio in general and not only in speech, which is important if you're working with music or if you're doing things that are more about noise and not specifically, well, anything that is in speech directly. What's not so nice about Viscol, and is really the main difference between the old generation and neural network-based ones that are in the three bottom columns, is that it's not differentiable. So we can't really use it if we want to add it to a loss, as part of a loss function when we're training a neural net. Moving forward, we can see MOSNet, which is a CNN trained to predict human MOS ratings from spectrograms. The big advantages of it are that there's no need for a reference while using it, and it is differentiable, as I said, a big plus. But it doesn't generalize well. This is true for all of them, actually. Most tests here demonstrate their ability and quality on a certain set of examples and tests, but it's really hard to know whether they're going to generalize to your own specific task. So it does require a bit of manual testing of the different algorithms to see which one is the right one for you and which one will do the best work. Going forward, CDPAM is a neural network that computes similarity score directly from two waveforms. So it requires reference, but also it's good if you're trying to compare a good or a different version of something to an older version. The advantages is that it works directly on the waveform. This is quite unusual, and uses no signal processing, so it can better learn human perception, as there are no preconceptions about how humans perceive sound. It uses self-supervised learning, so it doesn't need a lot of tag data and generalizes well. And the last one is Noresca, which is, they have an amazing paper, but they are not open source. They are good for research, but it's non-commercial. And it requires it does not require a reference, which is super cool, and does not use tag data in training. It is also shown to generalize well to many tasks and languages, and we know this because it was developed by Facebook, and they were able to throw enough computing power on it to test that out. So, coming back to our challenge, when we wanted to find the right algorithm for a comparison, we created a version of this table and just tried out the top three contestants that seemed for us that would do the job for our task. And as the field is progressing quickly in recent years, we're always on the lookout for new publications. This is very much happening these days, and it keeps on evolving, and it's fascinating to follow. This is the last slide, and I feel like this is where I should say some ending or closing remarks. We talked today about reducing the need to work with humans in the loop in our development process without compromising the outcome. And we talked about cases where humans in the loop are the ones we need to tag data, but also about cases where we're the humans in the loop because we constantly need to listen to the improving and evolving versions of the algorithms that we're building. I think I want to think you'd agree with me by now that this is not an easy task, but it is very much an interesting one. Thank you all for being here today. I had fun thinking about and presenting this talk.
Are there any questions? Any questions?
No, there's lunch. Come on.
I have like a really basic question, which I haven't. I think it's been a question even from the other talk. Like, when you're dealing with audio data, right? Like you say, you're computing similarity measures between two waveforms.
Yeah.
I can visualize that when I have like tabular data because I can see the features and things. But how does that work when you're dealing with how's audio data represented? How do you compute things with?
So many times I would show them visually, like I'll do the comparison on both just, listening to the two tracks.
Yeah.
And also, I would do a log mel spectrogram and sometimes subtract one log mel from the other to see a visual representation of what I'm doing.
Okay.
And also, I would sometimes listen to the two tracks in stereo, such that one track will be in one ear and the other one in the other. And then we're very well trained to be able to say whether we're listening to exactly the same track or whether there was a bit of a change. It feels like a glitch in the matrix when it's not exactly the same. You're like, wait, something is wrong here. And then it helps to pinpoint where exactly and what is it that I want to look at.
Okay, so is it fair to say then that there's no standardized kind of perception-based, in some sense, understanding the difference?
So
Is there a way to quantify it?
I mean, what I was showing here is a table that helps you to compare the tracks you're interested in and shift your attention towards where should you be looking, given the fact that you might be looking at many different tracks. But also, in the end, you will have to, even if you're doing all of that and you're already, shifting your attention to the places where there's a big difference between the tracks you're looking at, in the end, you will still have to listen yourself to whatever it is you're doing. There's no way out of this if you want good results. And everyone is doing it. I don't know anyone who's doing this without actually listening to a sub-portion of what they're doing in the end. It's really important.
All right. Thank you very much.
Thank you.
In the absence of any other questions, I think we can all just go to lunch.